Hello everybody and welcome to your notes on electricity. So in this video I'm going to go over some notes that you probably may have already done, but I just wanted to go over it with me here talking to you to maybe make a little bit better sense of it. And then after that I'm going to start talking about Ohm's law and just kind of like the basics of it, like what are the essential pieces that you need to know. And then in another video I will go over examples on how to do actual calculations with Ohm's law. So here we go. Every once in a while you'll see some essential questions. Those are the focus points of the notes. And then I'll also show you how your notes should be set up. But like I said before, you should already have this one down. If you don't, well, here's another focus point or essential question. So, what's happening in an electrical circuit and what can we measure about it? So you should have this question off to the left, and then your notes are going to go over here in this blank space. So here's an example of a complete circuit, one that has a battery and has the electrons flowing through it. So electricity is just the movement of charged particles, which is always going to be electrons. Electrons are the things that move in an atom. A circuit is the path of the charge that it follows. So a closed loop like this. So see how there's like one continuous path? Well, that's the circuit. So here's an example of a pretty straightforward electric circuit that many of you probably have at home. You've got an electric toaster. Inside of that, you've got some wires that go around. You've got a heating element that's in there. You've probably seen it if you look in there. It glows red. The switch is this little guy that you push down that activates the toaster, which really all you're doing is closing the switch, and then you allow the electrons to flow when that happens. Some electricity comes in through the plug, goes back out through the other side of the plug. Kind of like, well, cut off there, sorry about that. Kind of like a circuit of pipes. You could think about like the pipes in your home are similar to this, where you've got like a sink, you've got the water that comes in through the pipe, comes out the spout, and then goes down the drain back out, just like the electrons in an electrical circuit. Same thing goes for any of your other water using things in your home. Same thing goes here. So you've got, there are 3 holes in an electrical outlet. The big one doesn't really work for this part. It's for just in case something bad happens. But one of the holes is to allow electrons to go out, and the other one is to let electrons come in. So, what's happening in an electric circuit and how can we measure it? We're going to continue that going on. What happens in a circuit and what arrangement materials allow for charge to flow. So an open circuit is when the charges from the battery can't get back to the battery. So you've got a simple circuit here, the switch is open, there's no closed continuous loop that the electrons can follow. Closed circuit, charges can get back to the battery. So the switch is closed, and you can see that now if you were to trace a path through, it'd be able to get all the way through one side of the battery to the other. One example of this is like the simulation that I had you do previously. So we can see that this is an open circuit because this little guy is open here, and there's nothing happening. But as soon as I close this is now a closed circuit, and you can see that the electrons can now move. They're moving around the circuit, and as they go through the light, now that causes the light bulb to actually work. Electrons actually move much faster than this, but this is just slowed down so that you can actually see what's going on. And as you'll see in a moment in the next slide, instead of having it, instead of drawing circuits like this, it's common to see them represented with just symbols, because that way you don't have to draw batteries and light bulbs and wires every time. So you can see that the battery looks like this, the light bulb looks like that, and the wires are just straight lines like that. Alright, so back to it. So like I said, next slide is about how to draw circuits. So you can jot that down and then write down your notes off to the side. So here you can see there are two different representations. Oops, sorry about that. You can see that one is an actual picture and the other is what I would call a schematic. So a schematic is just a diagram of circuit. You use symbols and straight lines and right angles, and you try to draw it. It's easy to draw and it's much easier to read. And so here are all the different representations. A wire is just going to be a straight line. And again, you're always going to try to make right angles in your circuit. The battery is just going to be two lines. The side that's bigger is going to be the positive side, and the side that's smaller is going to be the negative side. The light bulb is just going to be a circle with some squiggles in it. The resistors are going to be just straight up and down squiggly lines. And then the switch is going to look something like that. So a conductor is going to be a material that allows electrical charge that you can flow through. Most metals, like copper or whatever, aluminum, any metal you can think of, are going to act as conductors because they have free electrons. You'll study that. Maybe you'll study something more like this in chemistry. Yeah, you will. That electrons are the things that can actually move around, and in metals they are even looser than in other non-metal materials. And then the opposite of that would be an insulator, where the material does not allow the charge to flow. So in most materials, electrons are tightly bound to atoms. So talking about your skin, talking about if you're holding a pencil right now, it's got tightly bound electrons. Pretty much most materials that are out there have tightly bound electrons. It's just the metals that typically have less tightly bound electrons. So wood, glass, plastic, ceramic, air, cotton, all those are conductors, or sorry, insulators. And then we have the famous semiconductors, which allow some of the charge to flow through some of the time under certain conditions. They don't conduct as well as most metals. Silicon is the most common semiconductor. If you bust open any electronic, you'll see like a green wafer. Those are your silicon wafers. And remember, so that somebody asked this before, silicon is different than silicone. Silicone has an E at the end, and silicone is more of like a rubbery substance that is very different than silicon. Silicone is very much so a insulator. So what can we measure about charge flowing? That's the next thing that you're going to want to write down. So here you can see an electrical schematic. You've got got two batteries here. Electrons go this way. You got your light, you got a switch. So you should already have this down, but this is like probably the most important part of the notes so far. So current is represented with a capital I, and it measures how fast the charge flows. The units that we use to measure current are amps or amperes, and that the variable, the variable is an I. This is confusing, but the variable is an I, but the unit is an amp, ampere, or you can just do an A. Resistance is another important part of circuits. The variable for that is a capital R. It's in opposition to the charge flowing. Anything that you can think of like uses, I'm trying to do air quotes here. I'm doing them in person, I promise. That uses uses electricity has some sort of resistance. So this light bulb right here has resistance. The units for that are ohms, or you'll sometimes see it with the Greek letter omega, which is again a weird thing, but hey, electricity is weird. Voltage, capital V for the variable. It's the energy difference between 2 points in a circuit. The units for voltage, again confusingly, is a volt or a capital V. So you're going to want to make flashcards for those or something and to try to keep all those straight because it can get confusing. So here's an analogy for you. Well, the battery adds energy. So it's kind of like you can think about the circuit kind of like this little animation that's right here where electrons are getting brought up higher. This isn't actually what's happening, but it's an analogy to maybe help you with this. The electrons are getting brought up higher when they come to the battery, and then they're moving along in the wire, and then when they get to the light bulb, energy leaves the system. So you can think about like the light bulb causes the electrons to go down this slope, and then they travel along back to the battery, and the battery brings them back up, and we keep going, and we keep going, and we keep going until the battery runs out of juice. Pump adds potential energy. At a waterfall, the energy leaves the system. So that's just what I was saying here with this animation. So charges have energy. Energy they gain or lose is called voltage, which increases at batteries, decreases at bulbs, and other things that have resistance. Here's another way to think about it. I like using water as a good analogy. Another set of notes, I'll talk about how it can be thought of like cars on a road. Electricity can be, but I'm going to stick with the water analogy for now. So voltage is the difference in energy between 2 points. So in this pipe right here, there's no height difference, so the water's not going to flow. That's like when you have a light bulb that's off. But if there's or no battery, notice how there's no battery there. So there's no voltage, no energy difference. But if you lift the edge of the pipe up, the water starts coming out of it, and that causes water to flow. Hey look, now there's a battery. That's like this pipe here that's now lifted up. The electricity is flowing because there's an energy difference due to the battery. Just like over here, you now have lifted up the pipe. So, how are they related? This is where the Ohm's Law stuff really begins. So if you already took notes on the other stuff and you felt like you're good, now is your time to start writing some stuff down. So what does Ohm's Law tell us? You saw a version of this in a simulation where it was V equals IR. You can also rewrite Ohm's Law as this. Ohm's Law is on your equation sheet, and you can also write it on a little cheat sheet and use it for your notes. So again, current is amps or a capital A, represented with a capital I in Ohm's Law. Voltage is a capital V. The units for that are volts or a capital V. And then resistance is a capital R in the equation. And then it's ohms or the omega symbol. So if you increase voltage, you get larger current. If you think about it like the battery is pushing harder, the electrons flow faster. So you got a big V, then you get a big I. Or a big voltage equals a big current. Increasing resistance causes a smaller current. It's harder to get the electrons through, so the electrons flow slower. So in this case, you get the R that's bigger, then you get a smaller I in the end. That's like the simulation that you guys saw before. You can do these notes if you want. I'm just leaving them on here so that way I'm going to come back to these when I actually start going through examples on how to do calculations around Ohm's Law. Okay, so that's coming up in the future. So next question goes here, and your notes go off to the side. So here's more on the water pump analogy. Okay, so we got that same simulation that I had going on before. So the water gains or loses energy based off of the part of the circuit that it's at. What if we wanted to make the energy gain or loss faster? There are two ways we can do this. And you got to think about this equation first, because that's what we're used to, the potential energy equation for the gravitational potential energy. Mass times gravity times height. So you can make the water flow faster, or you can make the water flow farther. And the way we can do that is, if you're thinking about the circuit, to make the energy give off faster, we can increase current or we can increase voltage. So that's like in our water pump analogy. You can either make the battery go or the water go faster. That's like increasing the current, or you can make the water fall further. That's like increasing the voltage or increasing the battery. How fast energy changes is called power. And that is where I'm going to end the notes here, because we're not going to talk about electrical power anymore. So if you want to, well, your next set of videos are going to be on how to actually do calculations related to Ohm's law. That's all I got for now. Thanks for listening.